captured effortlessly. That's the way it was. Happened so naturally. I did not know it was love.
This is our mass, and we'll also be calculating percent abundance. All right, so basically the formula that we're going to be using is the percent abundance so this is in decimal form. Multiplied by the mass. So we're just going to pretty much take the sum of these. So if you've never seen this before, this just means that we're going to do this for each isotope, and then we're going to add them all together. So let's go through this example right here. So basically our average, we're going to have to look to see what our average is. So we look up to beryllium and we say 9.0122 AMUs. This is the average, right? So this is going to be equal to our mass of this, so 10 AMUs times our percent abundance of this. And the way that we're going to solve for this is we're going to put in variables, and we're going to solve for the variables. So what we're going to do is say x and 1 minus x. So the reason that we can do this is because when we turn our percent abundances into decimal form, they're both going to add up to be 1, right? Between the two of them, they have to add up to be 1. Just as if we had two things making up 100%, they have to add up to be 100%. So in this case, we do x and 1 minus x. So we say 10 times x plus 8 times 1 minus x is equal to our average. Right? So now let's just work it out. So this is going to be 10x. This is going to be plus 8 minus 8x, right? Is all equal to 9.0122. We take it down another level, and we'll say, okay, these are both the same, so it's going to end up as 2x is equal to, we're going to subtract this 8 over. That's going to be 1.0122. So now we divide by 2. .5061. So x is equal to 0.5061. What we said? All right. So what would be our percent abundances over here? 50.6%, right? This is in decimal form. We use decimal form. And so now when we say what the actual percent abundance is, we have to multiply it by 100. So this would be 50.6, and what would this be? 49.4, right? Percent. A lot of people get tripped up here, switching to decimal form to use it there, and then coming back. So make sure that you do those two things. If it asks for percent abundance, you need to have it in percentage form, not decimal form. Any questions on this? So there will only be 2 on your test, only 2 isotopes like that. So if you get this problem, you should be fine. Okay, so let's go over some trends of the periodic table. There are several questions on this. And it's just, you guys will know most of it, and if not, you can probably think through it. So when we look at the periodic table, first let's look at groups. So let's name the groups in the periodic table. So first group, excluding hydrogen. Hydrogen's yellow because it belongs over here. So this first group is the alkali metals. Alkali metals. First group. Second group, alkaline earth metals. Alkali, alkaline. Here in the middle, transition metals. These green ones we classify as metalloids. So up here on the step, and if you look on your equation sheet, so if you look here on your equation sheet, it's got this nice little ladder here. That just indicates where all of these are. So, with the exception of aluminum, it's on both sides of this. This one and this one, excluding aluminum. So, these are metalloids. They share characteristics of both metals and non-metals. They're kind of in between. And then over here, we have non-metals, right? And then more specifically, we have right here, halides or halogens. And then this last one, noble gases, right? And so when we look at this, we know basically what they all exist as at standard conditions, right? So in standard conditions, these are going to be solids, right? They're both metals. These are metals. Metalloids, most of them are metal. Non-metals aren't going to be like metal, most of them liquid or gas. And then noble gases are obviously going to be in the gaseous state. So make sure that you know this, because there's a question on the test that kind of refers to which would have the lowest melting point, which would have the highest melting point, which has the highest boiling point. And you think about it, so he'll give you different groups, right? He'll say, well, what about this, what about this, what about this? Well, you can think, oh, well, which would have a higher boiling point, a metal or a gas? So noble gas or transition metal? Transition metal would have a higher boiling point, right? Because if it were really low, then it would already have boiled and it would exist as a gas. But the gases probably have a really low one, so in standard conditions they appear as gases. So if you know your groups, you'll be able to work your way through that problem. Next would be electronegativity. Yeah.
So, but if you have like you get out higher boiling point, is it like a you have an alkaline or an alkaline person? How would they move? You supposed to know that?
You don't have to know that.
What about like I'm sorry, what did you call those
So
one in between
metalloids.
There's not in between the metalloids and noble gases.
So there's non-metals and halogens. So non-metals, these are kind of included as non-metals, although they're more specifically halogens. Yes. It won't be a very hard question.
Question right here. So the melting point, would it be the reverse? Would it be the gases higher?
It would remain the same. So you could think of boiling point here, and then melting point here, and then boiling point here. So it's going to be the same trend.
Would you say that the general trend that it just decreases to the right, or decreases combustion, right?
I don't think you could say that for sure. I don't know. I'm not aware of a trend. But just know difference between gases and metals, and you should be fine. So gases have lower melting points, lower boiling points. So electronegativity, how does it trend? to the right and up. So fluorine is our most electronegative element. So to the right and up, we are increasing in electronegativity. Electronegativity is just basically how comfortable it is with having a negative charge, how much it likes negative charge. Now let's talk about ionization energy. Ionization energy is the amount of energy needed to remove an electron. So, what would you suspect would put up more of a fight to give up an electron?
Fluorine versus francium.
Exactly. So up over here, like the halogens, they really want one electron to become like a noble gas. So they're right there, about to become a noble gas. They just need one more, but then you take it away from them. They're not going to want that. So these have a very high ionization energy. It takes a lot of energy to take away an electron from them.
So it's a positive value, right?
Yes.
Energy has to be put in.
Exactly. So highest ionization energy up here, lower ionization energy as we go left and down.
How would like hydrogen compare to say oxygen?
Hydrogen is compared pretty closely with oxygen. So with its electronegativity, so I would assume that it would be similar for ionization. But I can't tell you that for sure because I'd assume that it'd be similar to the nonmetals. I'm not exactly sure comparing it to these other ones, but you should be fine. Yeah, question?
Do you see a bigger change in ionization energy as you move over a column or down?
I think it depends a little bit, but I'd say probably more so going from right to left. But just know that generally it increases going right and up, decreases going down and left. Okay, so now let's talk about atomic size or atomic radius. So the atomic radius decreases as we go from left to right. It gets smaller as we go across a road. But when we go down, it increases. So you could say that it decreases going right and up. Notice everything has done that. So right and up, we're increasing our number. So we're increasing in electronegativity. We are increasing in ionization energy. We are also, so now this time, we are going across and up to decrease in size. So right and up decreases atomic radius. And the reason that it decreases going across a row is because of effective nuclear charge. So over here we have a bunch of electrons in the fifth shell. So as we go across, we're not adding them further out. We're adding them in the same shell. They're just getting more packed together. We're also having more protons. So more protons with more electrons close to them, they're going to pull together like a magnet, negative and positive pull. They're going to pull together. So as we come across, we're going to have more of that charge, and it's going to shrink the atom as we go from left to right. So left to right and up is going to be decreasing the atomic radius. Effective nuclear charge only deals with going across a row. So now we are going to talk about electron affinity, which is the exact opposite of ionization energy. Now, if you look in your book, you might get confused because it has values. It has energy values to add an electron. So electron affinity, adding an electron, and you'll get positive and negative values, and it gets confusing to say, well, where is the electron affinity increasing? Where is it decreasing? We're going to say electron affinity in this class is how much something wants an electron. So it's going to have the exact same trend as electronegativity. So electron affinity increases as we go right and up.
So what's the difference between electronegativity and electron affinity?
So electronegativity is comfort with, so like how willing it is to have a negative charge, how stable it is with a negative charge. And electron affinity is accepting an electron, which is negative, so they're pretty much the same, but not exact.
Do we need to know the exceptions?
For nitrogen and all those.
Yeah.
You do not have to worry about the exceptions for defining.
So that's a negative value?
So over here, these are going to have negative values and such, but really all you need to worry about is where it increases and where it decreases. So electron affinity increases as we go right and up.
So if you were to say what has the highest electron affinity would be chlorine?
Yes. Exactly.
And we would exclude the noble gases because they're like.
Yeah, we don't really include noble gases in ionization energy. And you can also look, you may ask something like, which has a higher second ionization energy? So which is going to take more energy to remove the second electron? First ionization energy, remove the first electron. Second ionization energy, remove the second.
So would that be the alkaline metal?
So the ones with the highest second ionization energy would be the alkali metals, because you remove the first and it comes over here, and then to remove a second one, to take it out of this nice, comfortable octet and move it to this, it's not going to want to do that. So it would have a high second ionization energy. Okay, so we've gone through those, we've gone through natural abundance. So now let's go into the spectrum. So now let's go into the spectrum. So let's just pull up the spectrum.
Will we need to memorize like what colors are the spectrums?
You don't need to know specifically like wavelengths, but you should know the order that they're in hint. So let's get one. Yeah. So we look here, and let's just talk about a couple of things with this. So we look here and we see the wavelength on the bottom, right? So here's wavelength all the way across. This is just like a blow up of this little portion, which is the visible light spectrum. So you're going to need to know the intensity of these, which has the highest energy and which has the lower energy. So he'll ask you something similar to, what has the lowest energy, which has the lowest intensity? And we need to remember, let me see if it's on your equation sheet. I'm not sure if it is. So, let's see, he has it right here. So E equals H nu, right? So energy is equal to Planck's constant, H, which is given to you up here, 6.626 times 10 to the negative 34, times, this is our our frequency. So nu frequency right here, and this is wavelength, right? So energy, let's go back to our spectrum. So which has the highest energy? Gamma rays, right? Ultraviolet rays are strong, but they're just a little bit stronger than visible light. Infrared, a little bit weaker. Radar, FM. Can you imagine if FM waves were really strong and radioactive?
We'd all die.
There would be a lot of radiation in the air. So it makes sense that, so they have radar, they have like FM and TV and shortwave. You can just kind of bunch all of these together as radio waves. This is the first one that I've seen that has them separated like that. But basically all of these are radio waves. So
where's microwave?
that's a good point.
It's like,
It should be, yeah, it should be infrared and microwave. This one's kind of a weird one. Let's look at a different one. This one's backwards. This one's good. So we have gamma, then X-ray, ultraviolet, visible, infrared, microwaves, radio waves.
Do you think we need to know all of them, or just is it enough to know the gamma rays and the radio waves and just figure it out from there?
I would be able to put all of these in order, just because I'm not going to tell you which specific ones you need to know, but you'll have to differentiate between them. He'll give you like a list of 3 of them and say like which is the strongest or which is the weakest. So if you know them all in order, you should be good.
do we have to know approximate wavelengths?
You won't need to know wavelengths, approximate wavelengths. He'll just tell you the type of waves or the type of rays. So, all right. Okay, so we've talked about the spectrum. So you'll notice that, so this one only has wavelength on it, but let's draw it out with frequency. Okay, so we have, right here we have our spectrum, right? This is the little visible light section. So over here we have our weakest, right, our radio waves. And up here we have our strongest, the gamma rays. And so let's just do our trends. So wavelength is getting higher. So wavelength, remember, it's abbreviated like such. So this is lambda. Lambda is increasing. So wavelength increases as we go across over to radio waves. Our frequency, which is nu, increases as we go this way. So they're inversely related. As the wavelength gets bigger, we're getting a smaller frequency. Whereas if we have a gamma ray, it has a very high frequency, very short wavelength. So just as we were talking, E equals H nu. So as we increase our frequency, we are increasing our energy. So you could also say energy is going up on this side. All right, let's talk a little bit about emission versus absorption. So we have 2 types of spectrums, right? So it's going to be filled in with color, right? So we have this color, and we have 2 types of spectrums. So we have an absorption spectrum and an emission spectrum. So one is showing you what was absorbed, what was taken out. And that's going to be this one right here. So this is our absorption. And this down here is our emission spectrum. Does that have 2 M's?
Yep.
Yeah? Okay.
No, I have
Just 1 M? Okay, it looks kind of weird. Oh well, you get the point. Okay, so we've talked about emission and absorption. So now let's talk about n levels. All right, so we've talked previously about the Bohr model. I'm going to use it here to illustrate our shells, right? So we have all of these different shells that come out from the nucleus. These are, we'll say, orbits in this case with the Bohr model, where the electrons can be. So we're going to assume that it's hydrogen, so one proton in the nucleus, one electron out here. And so this is orbiting around. But if we put in a photon, so this photon comes in and it hits the atom, there's energy in this photon, right? So the electromagnetic spectrum is all energy. It's just energy traveling as a wave. It differs in how it travels because of the energy that is behind it. So this is coming in, and if we knew the wavelength of this, we would say, well, that's how much energy is coming into this atom. It comes here, it hits this, and the electron jumps, we'll say it jumps 2 shells out to N3. So we have N equals 1, N equals 2, and N equals 3. So it came in here, it was at 1, and it jumped to 3. So this amount of energy right here needed to go from N1 to N3 was absorbed from the energy in this wave. So this photon comes in, this wave of energy comes in. As it hits the electron, it takes that energy from the wave and uses it to bump its electron out to N3. So you're going to have to know how to use the Rydberg equation, which is on your equation sheet. So it's right here, top right. And the Rydberg constant is on there. So we have 1 over the wavelength is equal to a Rydberg constant times 1 over n1 squared minus 1 over n2 squared. So what this is telling us, what this equation is telling us, is the wavelength that was needed to make something go from one n level to the next. So let's calculate what the wavelength was of this photon coming in. So this photon came in, it hit it, and it went from N1 to N3. So let's calculate it. So we'll say, okay, what's our first? So we go from N equals 1 to N equals 3. So a lot of people get confused about which to put first in this. It will always work out if you put your smaller number first. So N1, 1 is smaller than 2, right? So in this case, we'd say, okay, 1 over N1, so 1 over 1 squared minus 1 over 3 squared times our Rydberg constant, which is 1.097 times 10 to the negative 19, is that what it is? 10 to the 7. 1.097 times 10 to the 7. What are the units on it? Meters? Okay. So meters and a lot of other things, right? But because this is in meters, this constant, if we use it, our wavelength is also going to be in meters. So you can either do it, you can do it a couple of different ways. You can either just do it in meters, calculate the wavelength in meters, and then convert it to nanometers. Or, let's see if he has it on here. No, he just has this one. So I would suggest doing it that way, because some of you might get confused if you convert the constant. So all of this is equal to 1 over the wavelength. So we'll do this down here. We'll say, okay, this is 1 over 1 squared, so 1 minus 1/9. We're going to get 8/9, right? times 1.097 times 10 to the 7 is equal to 1 over our wavelength. So how I do this on my calculator always is I multiply this number, and then on your calculator you can do 1 divided by answer, right? And if you do that, you'll find out your wavelength. Because if we say multiply this over and then divide these two back over, it's 1 over all of this. So basically our wavelength is equal to 1 over 8/9 times 1.097 times 10 to the 7. That'll be our wavelength in meters. So if you ask for it in nanometers or something else, you're going to have to convert it. Yeah.
So that reference constant in meters is to the 7, but in nanometers it's to the -2. Why is it to the -2? Because if you're going from meters to nanometers, would you multiply by positive 9?
No, because so in 1 meter there are 10 to the 9 nanometers, but we're at 7,
But it's meters.
or 10 to the 7, right? 10 to the 7 meters.
Yeah, that's like a large.
No, 10 to the 7th 1 over n.
Okay, so meters is in the denominator. Inverse meters, yeah. Thank you. So you run this calculation out and you get your wavelength in meters.
That's the wavelength of the photon coming in, right?
Exactly, yes.
The electron is
And this equation's just for hydrogen, right?
Just for hydrogen. We never do any examples that aren't hydrogen because it becomes a much more complex model, and this doesn't work with it. So this teaches us about quantized levels. So each of these levels has a certain energy, right? So to get to those levels, we need a specific photon with a specific energy to hit it, and then it will absorb the exact amount needed to go to this. Question?
There were some interesting questions about the Bohr model on our first test.
Yeah.
So we have to know all of that.
No, don't worry about it. Don't worry about the Bohr model. Yeah, so there's not a lot of like super deep conceptual ones. So you will remember though that so we have our levels, right? So n equals 1, n equals 2, n equals 3, n equals 4. So you notice they get closer as we go higher up. So this is energy on this axis, right? So an electron going from N1 to N3, if we compare the amount of energy needed to do that compared to the energy needed to go from 2 to 4, obviously the jump from 1 to 3 is a lot larger than 2 to 4. So this is just kind of a review. You guys remember this, right? All of these energy levels are kind of like this. So something is going to require more energy because, so this is our energy going up, going from here to here rather than from here to here because the gap is much larger here. How do we feel about that? All right? We also have to remember de Broglie's wavelength. So de Broglie, crazy dude, was like, hey, everything that moves has a wavelength. So everything has a wavelength, and we can calculate it. So previously I've had people calculate my wavelengths as I walked across the room. And for those of you that weren't there, you missed out. So we're going to do it now. So de Broglie's wavelength, it is on your sheet. It's right here. So lambda is equal to h over mv. This is not new. This is not frequency. velocity. So let's go over the units here. This is in velocity in meters per second. This mass is in kilograms. And this is Planck's constant. Or Planck's, as some people call it. And then it's going to give you a wavelength in meters. Which makes sense because we have meters over here, right? I'm not exactly sure how all the units cancel out. It must work with the constant somehow. But you'll get a wavelength in meters. All right, so my mass, so the mass of Tyson is about 70 kilos. And we'll say that I'm walking at approximately 1.5 meters per second. Sound good? All right, so my velocity is 1.5 meters per second. Or we could make it more interesting and we could say that I'm walking at 3.2 feet per second. I know you guys don't want to, but I'm going to do it for you. You just have to watch me. Okay, so we look over here and we have to get everything in the right units and then plug it in. So lambda is equal to Planck's constant, 6.626 times 10 to the negative 34 over my mass, I gave you, 70 kilograms, times my velocity. So we need to convert this to meters per second, right? So 3.2 feet per 1 second. So whenever it's per, it means it's in the denominator, right? So 3.2 feet per second. So let's convert this. So now we need meters up on top. So we're going to put in feet and meters. We want our feet to cancel and be left with meters per second. So we look at our conversion sheet over here, and we see that 1 foot is equal to 12 inches. Looks like we have to go to inches first. All right. So there are 12 inches in every 1 foot, right? So our feet cancel. We multiply this by 12, we get 36.6. Or wait, sorry, that's not right. Here, let me do it over here where there's more room. So 3.2 feet per second, right? And in every 1 foot, we have 12 inches. Feet cancel. This times 12 would be 38.4. So this is 38.4 inches per second, right? So seconds didn't cancel, just feet. And now we know that there are, let's see, 39.37 inches in a meter. So 39 point, what was it, 37? Inches in every 1 meter. So now our inches will cancel. 0.98. 0.98 meters per second. So now we have the correct unit, so now we'll put that up here. 9.8 meters per second.
Wait, no, it's 0.98.
0.98. Nice. 0.98. Don't do that on your test. So now we calculate this out. 9.66 times 10 to the 36, negative 36. So that's my wavelength in meters, right? So there's my wavelength, wavelength of Tyson.
Is there any way to measure rather than calculate the wavelength of the physical object?
I don't know. Good question. I doubt it, but maybe. Might be possible.
If Planck's constant, how did the joules cancel out?
So, let's see. So kilograms seconds, I believe, converts to joule.
I think right there, like energy, joules, kilogram.
Yeah, there we go.
Okay.
Okay, let's take a break. I'll show you this rad video of this eagle, which I thought was super cool. Again, I am a biology major, but you're probably going to laugh at this. Let's just go straight into orbitals. See, there's no questions on quantum numbers, and to be honest, quantum numbers are kind of useless. They only teach us about orbitals. So, we have our s orbital, right? We have our p. So we have p, then we have d, which is going to look like
Is that tetrahedral or?
so this is a very detailed drawing here. So there's your d orbital, and we go on to f, etc. But let's just go over the basics of these. So we need to know the number of orbitals. So the s has one orbital, right? So one orbital. P has 3 different orientations, right? So we have 3 of these. D, we have 5. So what does this tell us about the number of electrons that can be in them? Remember, each orbital can hold 2. One with a positive spin and one with a negative spin. So S can hold 2 electrons. P can hold 6. And this can hold 10. Which makes sense if you look at the periodic table. Because when we're doing electron configuration, we consider these 2 to be S's. So S has 2 spots, so 2 electrons, right? Over here, our P has 1, 2, 3, 4, 5, 6. Exactly the amount of electrons that it can hold. So it has 3 different orientations, and each one can hold 2 electrons. So a total of 6 electrons, which makes sense if you look up here, 1, 2, 3, 4, 5, 6. D, if you look between the S and the P, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons, because there's 5 different orbitals, and each of them can hold 2. What about F? If you forget about F, you can just look down here. This is the F. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. How many different orientations does the F? 7, right? Because each of them hold 2, so we get a total of 14 electrons. Pretty straightforward. So these are their shapes, and they all have different numbers of orientation. I believe we're going to go over electron configurations pretty much right now, but basically, as we fill, we're going to be filling these, and they also go in order of energy. So this is the lowest energy. So if they're all on equal n levels, we're saying 1s versus 1p versus, sorry, we'll say 2s versus 2p. No, we'll have to go even deeper, because D doesn't start until 3. So we'll do this in a second as we do the electron configuration. But you could say that a 3s is lower in energy than a 3p, which is lower in energy than a 3d. Yeah.
Do we need to know about nodes?
Don't worry about nodes. I really dislike nodes. It's like, wait a minute. I don't like them, but there's not any questions about nodes. So energies are in this fashion. So this is the lowest energy orbital, then P, then D. So now let's get into electron configuration. All right, so let's do electron configuration. We'll do one of a non-exception, and then we'll do one of an exception. So let's do sulfur, right? So sulfur, I love sulfur, okay? So we're just going to start from the beginning, right? So we start on the first row is just going to be, it's going to have an N level of 1. So we start with the 1s, we fill 1, 2 electrons, okay. So it's a 1s2. We then go to the second level, we start over here, so that's 2s1, 2s2. So we fill the 2s, and it can only hold 2 electrons, right? Up here, this superscript, that's the number of electrons in that orbital. So then we go to our 2p. So it's on the second row, and we go over here, 2p, it's going to fill all of these, right? Because sulfur's down here. So it's basically full here, full on the second row, and mostly full on the third row. So 1, we have full, 2, 2p, 6. We filled all 6 of those positions going across. Next we fill the 3s, and then we fill the 3p, but only 4 of the electrons will be used, right? Because as we come across here, 1, 2, 3, 4. These other 2 spots aren't going to be full, because we stopped here. So this is the electron configuration for sulfur. If we were to abbreviate it, we would say neon, 3s2, 3p4. And basically we're abbreviating all of this as neon. Because if you were to write the electron configuration of neon, this would be it. So we just abbreviate with its last noble gas, and then just go from there. So this is the abbreviated, and then this is the longer written out version. So now let's do an exception. Let's do copper plus. So we have to be careful with elements that are here. So copper, silver, gold, and then over here, chromium and molybdenum. So those are ones that you're going to have to worry about. And I'll show you why. Because as we go along, so I'm just going to write the abbreviated version. So we know that there are, so copper 2+, it's on this row. So I'm going to abbreviate with the row right above it, argon. So argon. So now we go to the next step. We go down here to the 4s. It's going to fill both of those. And then we get into the d orbitals. Remember, this is the d orbitals, these 10. But you have to remember, so with s's and p's, you can just take this number on the side and put it in front. But with d, it's this number minus 1. So we're going from a 4s2 to a 3d. And we would originally say, all right, well, copper, if it were just copper, we'd say 3d9. But we need to look at this exception, because these ones right here, they will take an electron from your S to fill the D. So copper, just by itself, is going to take one of these and put it over here. So you'll get a 4s1, 3d10. So that's just regular copper. It's going to take one from the s orbital to fill the d. So that's what copper and silver will do, along with chromium and molybdenum. They will both take one electron to either half fill. So molybdenum, so here's its D. Molybdenum would be like this, right? But it finds itself a lot more stable if everything is half full. So it will take one from the s orbital. So your s will look like this, and your d will look like that. So molybdenum and chromium are going to take one from the s and put it over here in the d. And copper and silver and gold are going to take from the s to fully fill their d orbital. So this becomes a 10. Now, if we turn this into copper plus, our new configuration, so we have to think here of the difference between core electrons and valence electrons. Valence electrons are the ones that are furthest out. Core electrons are closer to the core. Kind of makes sense, right? So we have here's our atom, and here's 1, 2, 3, and then 4. Your s orbital is on the 4th n level. It's further out. So here's n equals 4, and there's this 1 electron out here. 3 has all of the p electrons, all of the d electrons are in here on n equals 3. But this one outside, that's our valence electron. It's in the furthest shell. So 4 is further out than 3, so this is a valence electron. So when we ionize it, when we turn it to copper plus, we're going to be taking away 1 electron, and we always take from the valence. So you would be taking this. So for copper plus, this would be the electron configuration. Argon 3d10. So whenever you have an ion, do the electron configuration for the normal element, and then take one away from the valence. If it were copper 2 plus, we would take one away, we would turn this into 3d9.
But, so that would be the same thing if you're taking away from zinc or cadmium or...
Yeah.
But when you're filling them, so if you're filling them, then you put it into the 4s first.
Mm-hmm. So you fill it, you fill the 4s, you fill the 3d, and then you see if you need to take one away to make it half or completely full, and then you look at the charge to take away electrons.
But you only take away from the S if it can either be half for everything or full for everything.
Exactly. But then when you're looking at charge, then you will be taking from the S, just because it's the valence. So here's the question. How many valence electrons does chromium have? How many valence electrons? One valence electron. Because if you look at this chromium, it's going to take one from this 4s and put it in the 3d to make 4s1, 3d5. And your valence are your furthest out, so 4s, furthest out, so one valence electron.
And for manganese, it'd be 2 valence.
For manganese, it'd be 2. And this is why when you look at most transition metals, most of them have a +2 charge. Why? Because they'll lose these first 2 valence electrons.
Is the electron configuration for chromium, the CR, is that 4s2, 3d5?
Wait, chromium what?
CR. Oh wait, no, that's the fourth one. Oh, fifth one there. Okay. Sorry. So for manganese, it's 4s2.
4s2, 3d5.
It goes killed.
All right. So we've gone over that. We've gone over electron configurations, valence versus core. isoelectronic means that if you were to write out both of the electron configurations, they would be the exact same. So in other words, neon and oxygen 2- are isoelectronic. Because if you were to write them both out, they would have the exact same electron configuration. So I'll write it out for you. So we have O2- and neon. O2- is going to be 1s2, 2s2, 2p6. Neon is going to be 1s2, 2s2, 2p6. Isoelectronic. They have the same electron configuration.
So you could have ions that have the same number of electrons, but they're not isoelectronic because when you're taking them off, you take them from, say, the 4s shell instead. Couldn't you?
Yes. Yeah. It depends on the situation and what it is. If it deals with one of the exceptions, then you're just going to have to see. But basically, if you write out the electron configuration for both of them, and they're the same, then they're isoelectronic.
Will we ever be asked to say write a isoelectronic version of xenon?
It's multiple choice, so no.
Okay.
Bond length versus bond energy. Yes.
I thought that there was transported ones who were outside like that.
Yeah, so they're the furthest out. So when you abbreviate, not technically, but most of the time, they're just the ones that are on the furthest end level. So the ones that are on the highest end. So if we have something that's like 4s2, 3d, 10, 4p3, we're going to look at these two because they're furthest out, and this one's deeper in. So this would have a total of 5 valence electrons. So like we would have an abbreviation over here, but not technically all of them because these ones are a little bit deeper.
Which one would it come first, the 4s or the 4p?
From the 4p, because if you remember, p is higher in energy, so it will take the higher energy ones out first. Okay, so bond length versus bond energy. So we have two different molecules. We have this one that's got a big atom with a smaller one, and this one with between two smaller ones. Which has a stronger bond? A or B?
B.
B. Why? Because it has a smaller bond length. So when we get a small bond length, which is between the center of each atom, so basically you're adding up the two radius, or the two radii, that's going to give you your bond length. So we look at these two, and this one's going to have a stronger bond. It's going to be harder to break that because it's so close together. Which is specifically why FH, you would think, wow, that's an electronegative element. Why isn't it a strong acid? Because fluorine is so small and hydrogen is so small that it makes a pretty strong bond between the two. So it doesn't give up hydrogen like all of the other strong acids do. So bond length, as we get a smaller bond length, it's going to become stronger. Let's get into Lewis dot structures. You will have to draw one on your test.
What? I thought it was multiple choice.
No, you won't have to draw it, but you'll have to recognize it. Well, actually, take that back. You will have to draw it because he asks you specifics about the structure without giving you structure. So you have to draw it on your own and then figure it out.
How many problems?
I think there's only one.
Is it one problem here?
But that's assuming that you already know like structures of like NH3 and such like stuff like that that you've been working with a lot. It should come pretty easy and you won't have to really worry about drawing. So let's draw for C3H6. So what are we going to do? We're going to assume that it's a carbon backbone. So all the carbons are connected to each other. So carbon, carbon, carbon. Good? So we're going to say that they're all connected. Carbon backbone. You can always count on carbon backbones. Almost always. Now hydrogen. So let's go in and let's fill the hydrogens. So if you remember, each carbon has 4 valence electrons. So if we look up there, 1, 2, 3, 4, right? And it needs to obey the octet rule. Remember, octet rule, it needs 8 electrons surrounding it. Those include the electrons from different atoms. So, I'll draw this out to show all of our electrons. So we have a carbon here, it has 4 electrons, right? Carbon here, it has 4 electrons. Carbon here has 4 electrons. And then we have 6 hydrogens, which all have 1 electron. Alright, so we have these, and 2 electrons make up a bond. So here's a bond, here's a bond, here's a bond, here's a bond. Now we have to look at it and say, are we obeying the octet rule? No. So this carbon has 1, 2, 3, 4, 5, 6, 7, not 8. This one, 1, 2, 3, 4, 5, 6, 7, 8. Looks good. This one only has 7, so it's not good. We have to obey the octet rule with everything except third row elements. Remember, those can have an expanded octet. They can have more than 8. So when I say third row, I'm saying aluminum, silicon, phosphorus, sodium, chloride. So that row and below. So you're going to have to mess with this a little bit. And Chuni has mentioned before in the past that you know that it's an alkene if your number of hydrogens is equal to twice the number of carbons. So that's kind of a nice thing to know. So C equals N and then H equals 2N. That's an alkene. So this has 1 double bond or it's in a ring. So we look at this and we say, okay, well that's exactly what we have here, C3H6. If you don't remember this, you can just work with it for a while until it works. And so let's assume that there's a double bond. So we'll have a carbon, a carbon, a carbon. So let's assume that there's a double bond in here. Can we have a double bond to a hydrogen? No, because a hydrogen can only have 2 electrons max. So this one's using up 2 of its electrons here, this one's using up 2 here, 1 there. So it has 1 left, right? It started with 4. This one has 1, 2, 3, 4. This one has 1, 2, 3, 4. So now let's put in our hydrogens. 1 electron there. Are we obeying the octet rule? Yes, so we count around it, we say this carbon has 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Good. So this is a correct meter structure. If you drew something like this, that would also be correct.
So, in nature, when you have double bond, usually that means the bond is distributed equally. In this case, where you have an extra hydrogen after carbons, is that not the case? Is it can be different?
So basically, whenever we have a double bond like this, it's going to be bouncing back and forth. So you could say that it exists as this, and it also exists as, it would look like this, if I did
But
stick structure.
how would it do that when it has 3 hydrogens on that right-hand carbon?
The hydrogen shift.
The hydrogen shifting too?
Yeah. In organic chemistry, you'll learn about hydrogen shifts and methyl shifts. Methyl groups will also shift for a more comfortable conformation. So, Lewis dot structures. You're not going to have to do a hard one, I promise. The weird nitrogen ones, don't worry about it. So, exceptions to the octet rule.
Will we need to do one of those?
I don't remember. But if it is in there, it'd be an expanded one. He's not going to have to use it. So let's do this. Is this a valid Lewis structure?
Yes.
Why is it a valid Lewis structure?
Xenon flows through most.
Xenon is all powerful.
Xenon is all powerful. I don't know if you guys watch Xenon Girl of the 21st Century. Sweet show, right? So when we look at something, we're not just looking at the central atom. Although xenon's cool, we look at the other things and we say, do the other atoms involved, do they have to obey the octet rule, and are they obeying it? So we look here, this oxygen, if I were to draw in the lone pairs, it would look like this. So we look at the octet rules. Oxygen and chlorine have to obey the, well, chlorine does not. Sorry, I was thinking chlorine. So we look at this. Does this have 8? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And the chlorine has to have at least 8, right? Just because it's on the third row doesn't mean that it can have less than an octet. It means that it can have more than an octet. Why? Because our D electrons, those shells, begin on the third n level, right? We may not fill them till after 4s, but they're on n level 3.
We not exactly formula chart.
No.
We need like one to talk about that's a signal high level right there.
You have to build a
So now let's talk about electron group geometry and molecular geometry. So electron group, we're just looking at the steric number. This one's straightforward. Molecular geometry, that's where we get into number of lone pairs, right? So we look at this and we say, what is the electron geometry of xenon? Trigonal bipyramidal is correct. Because when we're looking at electron geometry, we're looking at the steric number, right? Steric number is the number of groups coming off of it. So it has one group here, one group there, and then 4 groups up here. So a total of 6 groups. And so when you draw it out,
Yeah, it's not
I'm hearing a lot of mumbles.
Is that an octagonal of 6?
No, it's wait, what was the question? It's trigonal bipyramidal.
I think it's trigonal bipyramidal.
Which Which one?
Is it octahedral?
It is octahedral.
Trigonal bipyramidal would be for 2 lone pairs and 4 bonded atoms.
You're going one thing down.
No, it's 5. Because you have the triangle at the bottom of 2.
Yeah, I
Things
think
at the top. It says 4.
Okay, so yes, octahedral.
4 axes.
Octahedral because the steric number is 6. So when we're looking at our electron geometry, we find the steric number, and then that steric number for 6, it would be octahedral. So yeah, that is correct. Once we get into things that have, so let's just look at H2O. What is its electron group geometry? So its electron group geometry, we have a steric number of 4, so it's going to be tetrahedral. But its molecular geometry is going to be bent, and that's what all of you guys like, bent. So water is bent molecular geometry, but its electron geometry is totally dependent on steric number. So we look here, steric number has 4 groups coming off of it, so 4 tetrahedral.
Quick question.
Yeah.
So, if it has 1 or 2, something that, if you have a central atom and 2 atoms bonded to it, the only way it can be linear is if it has 3 long pairs, right? So if that hypothetically would breaking nature, if there's only 1 lone pair, it would still be bent, right?
Yes.
Not as much, but it would be bent.
Yeah, it'd be bent.
If there were 3 lone pairs, it would be linear, right?
Yeah.
Because they would all go in the equatorial.
I want to say that it'd be tetrahedral if it had 3 lone pairs and 1 hydrogen.
But it's molecular geometry.
Well, if there's 4 different groups, you're not going to be
So
able to distinguish.
my question is, when can you get linear as an overall?
So linear, the only time you're going to see linear is without lone pairs.
Well, I think, no, like, if you had, like, when you have, if you had a T-shape, you have a steric number of 5, but 3 of them are electron groups, or T-shape lone pairs.
And then
you have
2.
the top and the bottom of you.
But yeah, but when we talk about geometry, we're including the lone pairs, so then we don't call that linear, then we call it trigonal bipyramidal.
The book says that. And that's like an hour today.
Don't worry about it. You don't have to get this deep into it. But always go with the book over me. Always.
Hey, Tyson, yeah, you need to know the bonding rules.
No.
Okay.
Okay. So let's jump on to. So we have electron group geometry. We just did. Let's talk about polarity. So. I'll give you a practice question here. Highest polarity, or we'll say the most polar bond. A will do O to H. B will do O to O. C, we will do C to H. D, we'll do S to H. I was thinking of giving you a really easy one, but decided to give you. So most polar bond, we're looking for a big difference in electronegativity.
There's a smaller question where it asks about which one makes up the strongest intermolecular forces, which the answer would not be the correct answer.
Strongest intermolecular forces, it depends on the entire molecule.
Yeah, like H2O versus lots S.
So hydrogen is similar to carbon in electronegativity, right? So which would be the most polar bond? Which would have the highest electronegativity difference? A.
Why not B?
Why not D? Or B? So B we cannot because they have the same electronegativity. This one, carbon and hydrogen, like I said, we practically consider this a non-polar bond because hydrogen and carbon are so close in their electronegativity values. So if we place hydrogen where carbon is, we want a big difference, and so hydrogen where the carbon is, oxygen would be really electronegative with carbon less electronegative, or we could have two lesser electronegatives, which would be S and H, which would give us a smaller difference. So OH bond is going to be our most polar bond.
So if there were FH bond, that would be the most polar bond?
FH would be extremely polar, yeah, about as polar as it gets.
So which would have strongest molecular forces, H2O or H2S?
Which would have more intermolecular forces?
Yeah.
I'd say H2O.
I would too. Smart word says because
Which has more intermolecular forces?
yeah, because they're like similar for all intents and purposes, but sulfur's bigger. So this is the one in the inversion, but I think at the end of the difference in electronegativity.
But if you had SH2, it couldn't hydrogen bond, which trumps the polar bonds of SH. So I would go with me over smart work on that one. Yeah, in the back.
Hydrogen bonding aside, does polarity determine
So a more polar bond is going to be stronger. Yes. There are other factors involved. So when we look at ionic bond strength and covalent bond strength, there are different factors. So for covalent bond strength, we're looking at bond radius, right? With ionic bond strength, we're looking at charges. So something that's 2 plus with something that's 2 minus is going to form a stronger bond than something that's +1 with -1. Size also comes into effect there, but primarily we look at charge for ionic bonding. Okay, so let's look at some molecules. So when we're looking at polarity, we're looking at a difference in electronegativity, difference in charge distribution. So, for example, we have, so what we always use for like polar, it's like NH3 and H2O. These are obviously polar. One, they have polar bonds, but when we're looking to see if a molecule is polar, we're looking at overall distribution of electrons. Here it has these electrons kind of grouped together, and this one has it apart from the other parts. So we're going to have a partial negative charge just because all the electrons are concentrated in these parts, and we'll have a partial positive down here by the hydrogens. So this difference is what makes up polarity of a molecule. Whereas when we have something like this, this molecule is not polar. Does it contain polar bonds? Yes, but it is not a polar molecule. When we look at the molecule, we're looking overall. And if you looked overall on this, all of its electrons are distributed evenly.
I thought we assumed that tetrahedral was always polar.
No, it's the other way around. The tetrahedral is never polar.
Thank you.
So for that tetrahedral would be polar if they weren't all the same round, right?
So it depends on if we're talking about molecular geometry or electron geometry. Because tetrahedral with lone pairs, like I said before, water is tetrahedral for electron geometry. but then it's bent for molecular. So I can't give a definite answer to that question, but basically just look at it, and if it has a lone pair, it's going to be polar. If it doesn't have a lone pair, then it's possible that it's not polar, but it can still be polar depending on what it's bonded to.
No, I know this probably isn't right, but if the hydrogen was like the chlorine, and to imagine it's not good anyway, would that make it not polar since they are not balanced?
So you're saying if we put a chlorine here,
Yeah. That's polar.
this would then become polar.
Got it.
Just because if you look around this nitrogen, you have something that's really electronegative with other things that are less electronegative. So you're going to get this electronegative element pulling a lot of the electron density towards itself, making it more negative.
And if you put two chlorines on there, it would still be polar, right?
Yes. It's only when everything around it is the same.
If you have things like cancers, so NCl3H or HCl3N, or so you have 3 chlorines and 1 hydrogen, and then never mind, it's not even important. Screw this stuff.
Chemistry's important. Okay, so we're about 2 hours through. We've gone through a lot.
Get low when the whistle go.
Valence bond theory. So you're obviously going to want to know hybridization. It's a big topic in chemistry. So we have, when we're looking at hybridization, the key thing that will tip us off is the steric number. You find the steric number, and it's super easy to find the hybridization. So let's do the hybridization right here for the nitrogen. It has a steric number of 4, right? 4 groups coming off of it. So we're going to say, all right, well, we need a total of 4. I'm not going to draw a 1 here, but if I did, it would look like that, and we would sum it all up to 4, right? But we don't draw the 1 in, so it would be, this hybridizes as an sp3. So we needed to make up 4 orbitals to make these sigma bonds, or to encompass the lone pair. And so we're going to get an sp3. If we get something that has a double bond, let's say we have this carbon going to, so in class the other day he did acetic acid, right? Acetic acid is going to look like this. So we look at this and he says, what is the hybridization of this carbon? So you look at it, what's the steric number? It has 1, 2, 3. So this is going to be sp2, right? Because that sums up to 3. We have 1 s orbital with 2 p orbitals. So basically what's happening when we hybridize orbitals is we take 2 things of different character, put them together, and we get something that's in between. So this carbon right here is going to have 3 sp2 orbitals. So we take 1 s and 2 p's, and we get 3 sp2 orbitals. And then these are then going to bond with the hybridization of the other elements. So this one's going to be sp3. Hydrogen you're never going to see hydrogen hybridized. Why? Because it only has one orbital. You can't mix one orbital with one orbital to switch it. So it's always going to exist as a 1s. I did this oxygen as an sp3. Why? Because its steric number is 4. So it's going to make 4 sp3 orbitals. And when these orbitals overlap, that constitutes a bond. So when they overlap, that's a bond. So this is a bond right here. This is a bond right here. But what gets complex is when we have double bonds, or when we have things that disobey the octet rule. So let's do an example of both of those in one. Let's do the one that I showed you before. What is the hybridization of the central atom?
SP3. SP2-3B. No, that's
Okay, so we look at this, right? And we say, all right, what's the steric number? 1, 2, 3, 4, 5, 6. So we'd say S, P3, D2. I'm not done. But we have 2 pi bonds here, right? So a single bond's a sigma, and when we see these double bonds, it means that one of them is sigma and one of them is pi. A pi bond requires an unhybridized p orbital. If we just used up all 3 of our p orbitals, there's none left to make the pi bond. So what are we going to do? We are going to use d orbitals instead of p orbitals, so that we have those p orbitals left out to do the pi bonds. So there's 2 pi bonds here, so we're going to take 2 p's out, and we're going to use 2 more d's. So this would be the correct electron, or the correct hybridization of xenon, girl of the 21st century, right there. Any questions on that? So we need unhybridized p orbitals to make pi bonds. So if you notice over here, we said that this is sp2, and that goes along perfectly. Why? Because it has 1 p left out to make this pi bond. So when you're doing carbons and oxygens, it's going to be like this. But if we get something that can disobey the octet rule, that can have an expanded octet, that's where you're going to have to watch to be able to shift electrons to the d orbital. Any more questions on that?
Are we going to have to specify like which row, like you have like the 1s?
So that's with, yeah, I don't think so. It's kind of hard when you include the d's. If it's involving s and p's, you could say it's like a 2sp2, p, because you used a 2s and a 2p to make the 2sp2s. But when we use d, we're using a 3d with other things. So I don't think you can do it with SPD when you include all 3. But if he has numbers on there, then go for numbers.
I have a question right here.
Yeah.
So over there in that example with the acetate,
Yeah.
if we were to name each bond individually, would they all be sp2 bonds, or would it just be the double bonds that would be sp3?
So if he asks for what bonds exist, what hybridization exists between the carbon-oxygen bonds,
right,
you would have to list several. So we would say this is sp2. It's having all these sp2s come out. So this carbon to oxygen, the carbon to oxygen, like here to here, was an sp2 to an sp3. So this is sp2 to sp3. The carbon double bond to oxygen is going to be an it's going to be a P to a P.
That's for the pi.
So this is the double bond, right? The pi bond.
And what was the first one?
I guess I should show you with that. Then we say C to O, pi bond is P to P, and then that other one's going to be exactly the same. Well, no. Then we also have the carbon to oxygen sigma, that would be sp2 to sp2. So those would be like possible ones, but you're going to have to list them for each individual one.
How would you figure that out?
So you look at the hybridization of each of them. So the sigma bond is always going to be hybridized to hybridized. But when you have a pi bond, that's going to be just P to P. Always. So in this case, I looked up at the oxygen. I know that there's two lone pairs here. So
do we specify 2P to 2P? Because then
yeah, that would be more specific.
okay.
You could say 2P to 2P. And with all of these, you could put a 2 in front.
So what would the xenon to oxygen be? Would that be sp4 to sp2? Got it. With the P to P.
With P.
Why do you have the 2 in front of the P?
Because we used a 2s orbital, because carbon's on the second row, so we used its 2s and its 2p combined to make the 2p, 2sp, 2, whatever comes out. Any other questions? Nope. Okay. So we've gone over that. Molecular orbital theory. This one's scary to people, but it doesn't have to be. If he made you draw out the orbital diagram, it would be tougher. But because he doesn't, you just fill in the number of electrons.
Do you have to be able to calculate the band gap?
No. I threw that up there because I wasn't sure if I kind of wanted to teach it, but I don't think it's on the test. But I'll review. You don't have to calculate it, for sure. But I'll review metallic bonds just a little bit.
What about bond order?
Bond order, yes. And you'll be taking that from molecular orbital theory. So molecular orbital theory, basically we have, you'll have a diagram. Here, I'll show you what a diagram is, just to jog your memory. The molecular orbital diagram. That one looks kind of close. He has them like colored, but remember it's this middle segment. You won't be dealing with these outside segments. That's just how they built it. But it'll be something similar to this. You'll be going from sigma, sigma star, etc. So
will that be given to us, or do we need like memorize?
that will be given to you. You will have something similar to this. And basically what you're going to be doing is adding up your number of valence electrons. You'll take your number of valence electrons between both elements. Molecular orbital, that means we're going between two atoms forming a molecule, forming a molecular orbital. So let's say, for example, that it is oxygen. We're going to say O2. It's going to say, what is the bond order of this? So we would look, and we have, first we have sigma, then we have sigma star, then we come up here, we have sigma, pi, and then pi, sigma. So this is what your orbital would look like, your map, your diagram. We'd say oxygen to oxygen. Okay, well how many total valence electrons do we have?
12.
12. And this is where you have to watch yourself, because, for instance, on this, it has the 1s listed right here. It's really hard to see. You can see the 1. It's talking 1s, and then 1s down here, 1s up here, and, sorry, 1s and then 2s. You'll have to watch, just because if we're going to be doing this, say for 2s, 2s, 2p, 2p, 2p. So we're looking specifically at valence electrons because we're starting at 2, which is where both oxygens are, right? If he had something down here for 1s and 1s, so sigma star 1s and sigma 1s, sorry, that's very low on the board, then you would have to include all of the electrons because we're starting from n level 1. We're starting with the 1s orbital. But I believe the one on the test starts at 2s. It starts at your valence electrons. So you count your number of valence electrons. Oxygen has 6 valence electrons, right? But we have 2 of them, so a total of 12. So we're going to go along and we're going to fill it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is how you would fill it up, right? But how do we determine bond order from this?
Bonding minus anti-bonding divided by 2.
Exactly. So we're going to take our number of bonding electrons minus our number of anti-bonding or non-bonding. So anti-bonding electrons. And then we're going to take that number and we're going to divide it by 2. So we look at this and we say, all right, how many bonding electrons do we have? Those are the ones without the stars. So we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 bonding minus how many anti-bonding? 1, 2, 3, 4. Divided by 2, and we get 2. 8 minus 4, 4 divided by 2 is 2. So the bond order for O2 is 2. So this is equal to our bond order. BO, yeah. So if we were to look at the molecule O2, what would it look like? How many bonds would be between them? 2 bonds, right? So bond order also tells you the average number of bonds. And since there's 2 atoms involved here, you're going to have 2 bonds between the 2 of them. Make sense? All right, let's push on. On to naming organic compounds. You will have to name one organic compound. It's not a very tough one, I promise. So, do you guys need a break?
No.
All right, we'll just go. We'll pound through. All right, so when we're naming a molecule, we're going to look at its longest chain first, right? So the longest chain is our first step. We need to identify the longest chain. And you're going to need to know basically up to like 7 or 8. You'll need to know. So 1 is meth, 2 eth, 3 is prop, 4 tetra. Sorry, not tetra.
4 is tetra.
4 is bute.
Yeah. And for
5 is pent. 6 is hex. 7 is hept. 8 is oct. I'm out of room and you don't need to know more than that, so we'll stop there. So this is our prefix, right? So this is a prefix. And our suffix has to do with if there's a double bond, just all single bonds, or if there's triple bond. So if they're all single bonds, we're going to have ane. If there's at least one double bond, it'll be ene. If there's at least one triple bond, it'll be an ine. So we're going to look at the longest chain. So let me draw a molecule for you. Let's name this. So we look at it and we say longest chain. How long can it be? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Looks like 5's our longest chain. 1, 2, 3, 4, 5. So this would be a 5. So it's a pent. Are there any double bonds? No. So this is a pentane, right? Now we need to look at the functional groups coming off of it, right? So we have one here and one here. How are we going to number this? From right to left. Because if we number from left to right, our first functional group will be at carbon 3. Over here, if we number it, it will be at carbon 2. We always pick the one with the lower number. So we're going to say 1, 2, 3, 4, 5. So we have a 2-methyl and a 3-ethyl. So you just add the YL to these, right? So this one has 2 carbons coming off of it, 1, 2, coming off of the main chain. This carbon counts as the main chain, so we count off of it. 1, 2, 2 being F. Since it's a functional group of just carbons, ethyl. This one has 1 carbon, methyl. So now we're going to put all of it together, and we're going to say that it's a 3-ethyl, 2-methyl pentane.
Is there any particular reason why
I put it in alphabetical order.
okay. Is that what
That's a general rule, but when you come to naming, you'll see across universities that some people will use different.
And if it's multiple choice, it will just use
Yeah. More correct at this university to have the ethyl before the methyl.
Are there any compounds or dashes?
You're just going to be doing an alkane. This should be pretty easy. Okay. So metal bonds, metallic bonds, when we have a conduction band or a band gap, that's going to increase our ability to conduct electricity. Basically, we're making more room, we have more empty orbitals that electrons can run through. So that's conduction. It's able to take more electrons through it because it has space for it. So that gap is bigger.
So when it says band gap, that doesn't refer to the gap between the valence band and the conduction band. That would be, because if that gap's bigger, then it becomes harder, right? So the band gap, is that within the conduction band? Or is that the gap between?
I guess I should have just said conduction band.
Okay.
It's the conduction band gets bigger than conduction gets bigger. It's more conductive. Okay, so we've named these. Let's get into intermolecular forces. All right, so we have a couple different types of intermolecular forces, right? Guess I could have used that big one, but okay, so intermolecular forces. I'm going to list them from the strongest to the weakest. So our strongest is ion dipole. Next would be hydrogen bonding. Then dipole-dipole. Then we have dipole-induced dipole. And then at the bottom we have London dispersion, right? Due to our lack of time, I'm going to focus on 3. Ion dipole. It's between something that has an ion, it's between an ion and something that has a dipole. So, for example, we have K plus and OH minus, well, water. We put it in there. This is polar, it has a dipole. Dipole, polarity, same thing. This is polar, this is an ion. They come together quite strongly. So that's our strongest intermolecular force. So if I were to put KOH in a, or we'll say I put KCl, potassium chloride in water, what is it that makes it dissolve? This ion dipole force that's happening within the water. So the water comes up next to it, it's got that strong force, so it pulls them apart. That's why ionic compounds are almost always soluble, because these ions that are together, they get in the water and there's this strong attraction between the water and the ions and it pulls it apart.
So it's between an ion and a molecule and particle force and not an intermolecular force?
I think they generalize it all into ion dipole. You're right, this is not a molecule, but like this same interaction happens with ion, so polyatomic ions.
But it was part of a molecule.
So why is what?
It was part of a molecule.
It was part of a molecule, but I guess the interactions between a particle and a molecule. So, but we include them all as ion dipole. That's a good question, though. Yeah. No. Well, yeah, they'd have to be.
They break down the ion.
Was that just because there are more water molecules?
Yeah. Plus, you have the fact there are a lot of waters that are all pulling at it. So it kind of breaks it. It kind of goes into hydrophilic versus hydrophobic kind of thing. But it's a good question. I'd have to look into it more. Hydrogen bonding. So for hydrogen bonding, we have nitrogen, oxygen, and fluorine, right? So our components to make a hydrogen bond, we have a lone pair from the oxygen, so it's the oxygen, the nitrogen, or the fluorine, and it is touching a hydrogen that is then attached to a very electronegative element. I write X here because X could be either oxygen, fluorine, or nitrogen. So, in order to have a hydrogen bond, we need all of these pieces of the recipe. We need a lone pair on one of these electronegative elements, and we need it to be, and then we also need a hydrogen connected to one of these elements as well. So, if you're looking for what can do hydrogen bonding, you're going to be looking for these pieces. Does it have a lone pair on a nitrogen, oxygen, fluorine? Does it have a hydrogen coming off of a nitrogen or oxygen or a fluorine? So, for example, if we took this molecule right here, can this hydrogen bond?
Yes.
Yes. What about if I turn these into chlorines?
Yeah. Oh, yeah.
So the nitrogen has a lone pair, but we don't have any hydrogens that are attached to oxygen, fluorine, or nitrogen. The hydrogens are all attached to carbon.
What if a hydrogen from an H2N came by and like one of the H's from that molecule touched that nitrogen? Would that still be
Then those two could do hydrogen bond.
Right.
But if we just bring up one molecule and we say, can this hydrogen bond? We're talking about with itself. So his question was, if something comes along, say an NH3 comes along, these two could do a hydrogen bond. But your questions are always, or almost always, can this hydrogen bond? So it's just referring with itself. So if you had a solution full of this, could it do hydrogen bonding? And for this one, it'd be no. So now let's go to London dispersion. So for London dispersion, what factors do we have? What makes something have more London dispersion forces? Size, right? So if we're looking at sizes, something that's bigger is going to make more London dispersion forces. And the reason behind that is London dispersion is basically we have, we'll say, two atoms here. And there's all these electrons in here moving back and forth, right? But if you took like a picture at just a split second, you would see, okay, well the electrons are moving as this wave, and it may come this way, and in that brief second, most of the electron density is over here. So you're going to have a partial negative charge. In the next, like, millionth of a second, it's going to be moving back. It's constantly moving. But if you get two things next to each other, and you get those two in sync, you're going to have a temporary dipole made there. So this negative is going to be next to the positive. And so they're suddenly attracted. It's very small, and you can imagine that it's even more difficult if you have very small atoms. So when we're looking at London dispersion, you're looking for surface area. So something that has more surface area, like this, is going to be able to interact with other molecules to have a lot of London dispersion, whereas something like this isn't going to be able to work very well. Is there a question? No? So we're looking at size. And when we look at intermolecular forces, that's a big factor behind melting point and boiling point. So if something has strong intermolecular forces, it's going to have a higher melting point or boiling point. For example, H2O, right? What intermolecular forces does this do? What's its highest? Hydrogen bonding, right? So when it's in solution, when we have a bunch of water all together, we get all these hydrogen bonds happening between molecules, and that's what's holding it all pretty close together. That's what's making it stay in liquid state. But as we turn up the temperature, we're putting more energy into it, and once we bypass the energy of these bonds by putting more heat into it, we're going to break the intermolecular bonds, and it's going to boil and turn into a gas. These are now free to separate and go their ways. So basically the moral of the story, higher intermolecular forces, higher boiling point, higher melting point. Because if it has strong forces, you're going to have to put in more temperature to make it melt or to make it boil. So it doesn't just have to be for molecules, you could also do it for atoms. So which would have the highest boiling point? Chlorine, bromine, or iodine? Iodine, because it's the biggest. So it's going to have more London dispersion forces. Because chlorine, bromine, and iodine by themselves, they don't have any other intermolecular force. It can't do a dipole-dipole interaction. It can't do ion dipole because there is no dipole anywhere. So it can do London dispersion. Everything can do London dispersion. So we look at that and we say which has the highest intermolecular forces? Iodine because it's biggest. Okay. So we've done hydrogen bonding. Hydrophobic. Is hydrophobic polar or non-polar? Non-polar. So hydrophobic is non-polar. Hydrophilic, polar. So phobic, it's afraid of you think of hydro, you think of water, and so it's afraid of water. Why? Because water's polar and it's not, so it doesn't want to get near water. Hydrophilic, it enjoys being with water. It is polar as water is polar. Density. So our density is equal to our grams, or our mass, per volume. In most of the case, it'll be grams per milliliter. But just as a general rule, it's mass over volume. So there will be quite a few questions on this test. I haven't really done any sample problems because I feel like you guys understand them. It'll be converting from how much of this do you need to produce this much of this. So there's a lot of things like that, and he's going to incorporate density in that. He'll say the density of this is, we'll do a quick example. We'll say, we'll do H2 plus O2 goes to make H2O. First off, you're going to make sure that your equation is balanced, right? Every time you see an equation, make sure it's balanced. That's how they love to steal points from you. Make sure it's balanced. And then I'm going to tell you that the density of hydrogen is equal to, so this is a gas, right? This is a gas. So the density of hydrogen gas is, we'll say, 3 grams per milliliter. So how many milliliters? So now the question would be something like, how many liters of H2 are needed to make 50 grams of water? So this would be a sample question. It's something where he's using, you have to get your balanced equation and then set up the molar ratios here. And then you're going to be using your density to figure that out. So we know, okay, 50 grams of water, that's how much we need to make. So how many moles of hydrogen am I going to need? And then when I know how many moles of hydrogen I need, I can figure out how many grams of hydrogen I'll need. And then I can figure out how many milliliters I need, which will then give me the number of liters. So I'll do this one real quick. All right, so we need to make 50 grams of H2O, right? So we're going to convert that to moles. So there's 18 grams in every 1 mole of H2O. Grams cancel. 50 divided by 18, we'll say it's like 2.4. I don't know. So 2.4 moles of H2O. So how many moles of H2 are we going to need? 2.4. 2.4. So if you were to write it out, you'd say, all right, this is how many moles of H2O we have. We set up our molar ratio, and we need to find out moles of H2. And we want moles of H2O to cancel, so it's 2 moles of H2O to every 2 moles of H2 multiplied by 1. So basically, we're left with 2.4 moles of H2. That's how much we need. So now we're going to figure out how many grams that is. 2.4 moles of H2 is equal to 2.4 grams of H2. No, that's not right. It would be equal to 4.8 grams, right? Because it's H2, 2 grams per mole. So 4.8 grams of H2 is what we need. And we need to figure out how many liters that is. So we want grams to cancel. So what we're going to do is we're going to flip this. So now it's going to be, for every 3 grams of H2, we have 1 milliliter. So we then divide this by 3, which would be 1.6 milliliters, right? Grams cancels. And we convert this to liters, right? Because I asked for the answer in liters, and you get 0.0, 1, 2, 3. So there's our answer. 0.0016 liters. So with density, feel free to flip it. Or if you need to change the units, say we had like kilograms over here, we could say, all right, well this is 0.003 kilograms per milliliter. You can mess with it like that. Just make sure that you're doing your conversions correctly.
What are the tests we had like prior to questions where you convert it like centimeters and deciliters? Like I didn't know. Or we need to know those.
I don't remember anything being crazy. You should for sure know at least micro and milli. Maybe mega too. But I don't remember anything being super crazy on it. Yeah.
What about nomenclature?
Nomenclature?
Like, is he gonna say like, phosphate without actually saying it's CO4 3 minus? Or would he actually give us?
I think there might have been 1 or 2, but they're not the weird exceptions.
One's like acetate, something like that.
Yeah. So I would know acetic acid because he always uses acetic acid. I don't remember if it's on there, but he uses that example a lot in class. So I would know acetic acid, benzene, and then just know your basic rules for naming compounds. The rest should be fine.
Acetic acid is CH2O.
Yeah, so it always helps for me to draw it out, and then I count it. So we have 3 hydrogens coming out here.
Yeah.
So it'd be C2H4O2. Sometimes they write it out CH3COOH. But just know how many carbons and how many hydrogens are in it. All right, let's continue. So you're going to make sure that you know how to balance reactions. Combustion reactions, you're going to have to do that. So I don't remember any fuel value or fuel density problem. It just deals with your delta H of combustion, right? So with combustion reactions, you're always going to be balancing. So let's combust benzene, C6H6. We combust it, so it's with O2, and we produce CO2 plus H2O. We balance out, we say 6. There's 6 of these. 6 hydrogens, so we form 3 of these. We have 6, so that'd be 12 oxygens, plus 3, so that'd be 15 oxygens, so this would be 7.5. This is not an even number, so we're going to multiply everything by 2, so 2. 15, 12, and 6. So now we have a balanced reaction, and he may say something like, he'll probably ask you to go between these things. He'll say, how much oxygen is needed to fully combust, we'll say 36 grams of benzene. So how much oxygen is needed to fully combust? So to fully combust means that we have the proper amounts for it all to react. So we're just going to be using molar ratios here. So you're going to find your number of moles of benzene, and then use the molar ratio, say, well, for every 2 moles of benzene, I need 15 of these. So you're going to go to moles of C6H6, and then you're going to multiply that over to moles. So we want moles of C6H6 to cancel, and we want moles of O2. So this cancels. We're left with moles of O2, which we can then multiply. So for every 1 mole, we have 32 grams. And then we can find out how many grams of oxygen we need to fully combust it. So a lot of this bouncing back and forth. Let's see. Percent mass. Let's do this problem right here. There is no calorimetry.
Yeah.
But there is one, it's kind of similar, we'll do it in a second. It's not a calorimeter. Percent yield, I can't remember if it's on there, but it's likely to be. Percent yield, so remember percent yield. So your percent yield is equal to your actual divided by your theoretical. Times 100, right? Where everybody gets tripped up is they think they don't have enough info to calculate this. When we look at theoretical, that's doing what we just did over here. They give you an amount of your reactant and you predict the amount of product. Off of the mole ratios, that's your theoretical. That's how much you would get if everything reacted. Your actual is an experimental value that has to be given to you, or maybe he gives you the percent yield and info to calculate the theoretical, and then you can then calculate the actual. He will always give you info. Either he'll give you the 2 variables, or he'll give you info to calculate the theoretical, and then give you like the actual and ask for the percent yield. He'll always give you 2, and you have to come up with the third. All right, let's do this problem right here. A compound is analyzed and found to contain so much nitrogen, so much oxygen, and hydrogen. So our carbon, nitrogen, and hydrogen, right? So carbon is 35.66. Nitrogen is 45.10. And hydrogen is 16.24. Did I write that down right? All right, so these are the percent masses. How do we find percent mass? It's the mass that that element is contributing compared to the mass of the entire molecule. So let's do a quick example over here. We have C2H6. The weight of this would be 24 plus 6, so the molecular weight is going to be 30, and our hydrogen is only giving 6 grams, right? So 6 divided by 30 times 100 is going to be equal to the percent mass of hydrogen. how much mass does hydrogen contribute divided by the total. So that's your percentage there. So when we're doing empirical formulas, when you are doing an empirical formula, be 35.66 grams. So we're going to act like it's a 100-gram sample. If it's a 100-gram sample, 35.66% of that is going to be 35.66 grams. So basically, you convert all of these to grams. We are then going to convert them to moles, right? So let's convert these to moles. All right, so we have 35.66 divided by 16 gives us 2.2. Oh, sorry. I thought I was on oxygen for some reason. 35.66 divided by 12. We have 2.97 moles. Here, 45.10 divided by 15. 14. Thank you. 3.22. And hydrogen. Wait a minute. This is coming out weird.
Yeah, because it's 3.
I calculated this one. This one should be good. 45.10 divided by 14. Okay, it says 3.22. We will keep going with this. And then this is going to be 16. So it's this divided by the mass of that is just going to be the same, right? So 16.24.
Percentages are just a little off.
Are the percentages off a little bit?
It's just because
Do they not add up to 100?
it's 97.
It's 97?
Yeah, because you end up with C and H of hydrogen.
No, he's got them right. That's the problem.
Well, let's just continue with this. So, we're now going to divide all these by the smallest. So what's our smallest here? 2.97. So we'll divide this by 2.97. We get 1 here, so 1 carbon. We divide this by 0.297 or 2.97. What did we get? 1.08. And then this divided by 2.97. 5.5. Okay, so this is going to work out. So now, when we look at this, these aren't all whole numbers, and they won't be usually, except for the one that you divided by itself. And things that are at like 5.5 or 5.25, close to like a number that you could multiply to make it whole, then that's feasible. Something like this, we're just going to consider being 1. So right now, our ratio would be carbon, there'd just be 1 carbon, right? 1 nitrogen, and then 5.5 hydrogens. So we're going to multiply the whole thing by 2 to make them work out. So it'd be C2N2H11. So this would be our answer. That's our empirical formula.
They gave you like the molecular mass. How do you convert that into like molecular formula?
Perfect question. So, he then may say, all right, the molecular weight of the compound that I'm looking for has a molecular weight of such and such. So let's mainly what you're going to be looking at is the weight of your empirical formula. So in this case, it'd be 24 plus 28. So 24 plus 28, 52 plus 11, so 63. So we have 63 grams per mole of our empirical formula. He then may tell you or give you info to say, all right, the one that I'm looking for has 126 grams for every 1 mole. The molecular formula has this. What molecule is this? So then you multiply all of these by 2, because this times 2 equals this. So you'll multiply everything by 2, and it would be C4N4H22.
You always list them in that order, carbon.
Generally, you do carbon first, and then nitrogen or oxygen, and then hydrogen. Well, actually, no. Don't worry about the trend, because it goes carbon, hydrogen, oxygen for other things. All right, so there's that. State functions, remember state functions are when we have a delta symbol. If there's a delta symbol, state function. Heat of combustion. So that's just your delta H of combustion. So if they tell you 36 grams of this produced this much energy, you could divide how much energy was produced by the number of grams combusted. Say the heat of combustion is so many joules per 1 gram. All right, so when we have so I just wrote G, S, and H. That's obviously Gibbs free energy, entropy, enthalpy. And there's the basic rule that applies to all of them, which it is sum of the number of moles times the whatever in this case. I'll just put X. X can equal our delta H of formation. It can equal our delta S naught or our delta G naught. So the sum of our products minus the sum of our reactants, right? Again, I bring up the importance of knowing that your equation is balanced, because that n is going to play a factor. Because that n is the coefficient on your equation.
What does the x equal?
So the x, I'm just saying it could be delta H, delta S, or delta G. Because if you're calculating for your delta H of reaction, you're going to be using your delta H's here. But if you're calculating your delta S of the reaction, then you're going to use your delta S naught values right here.
Which are given normally. Right?
Which are given, yeah. You're not expected to know that.
How do you find n again?
And n is number of moles.
Number of moles. Got it.
So your products and your reactants. So this is the sum of all of them, of your products. So if you have 2 products, and there's 2 moles of one and 2 moles of another, you're going to have 2 times the delta S naught of one of your products plus 2 times the delta S naught of the other product. And when you add those 2 together, that's the sum of your products, and then you're going to subtract the sum of your reactants. Okay.
On the last test, you had us use bond energies for a couple questions. You gonna ask about that?
No. All right. PV equals nRT. It's a beautiful equation, and it works. Except if we're dealing with under certain conditions. And those conditions are high temperature and high pressure. At high temperature and high pressure, gases begin to act non-ideally. So, and that's just because at high temperature, things are moving around a lot. High pressure, so they're really jammed in there. These things are going to be bouncing around. When they hit each other at such high velocities, you're going to have more interactions, and it's going to throw off your pressures, your volume, and such. So, PV equals nRT, except at high temperature and pressure?
High temperature or pressure?
It's relative. We don't really have a specific range.
That's gonna say at high temperature, or how is it coming from?
When you say it's ideal.
Gases behave non-ideally at high temperature and high pressure. Mole fractions and pressure. So, you need to know mole fractions and pressures. So it's called Dalton's law. You don't need to know that. But basically, Dalton, what he says is that our mole fraction, which is often abbreviated like this, times our total pressure, P tote, is equal to the partial pressure of that gas. So, let's do an example. You have a container. A sealed container, it's at 36 ATM. It's extremely pressurized. So we have two different gases in here. We have 3 grams of O2 and we have 10 grams of N2. What is the partial pressure of O2? So this is where we need to know our mole fraction. We know our total pressure, right? Total pressure, 36 atmospheres. Mole fraction, we're going to have to figure out how many moles we have total, and we're just going to divide by the moles of one of the substance. So, for example, for O2, we'd say moles of O2 divided by total moles. So that's going to be equal to our mole fraction for oxygen. Let's just say that we don't really have time to calculate it, but obviously you could go from 3 grams of oxygen to the number of moles of oxygen. Same thing with N2. You find that out, we'll say it's 0.30. So we multiply this across and we'd say, okay, this is equal to 10.8 atmospheres. So this is the partial pressure of O2. And then if you did it for N2, they should both add up to be 36. So each of them are contributing an amount of pressure, and it's directly related to its mole fraction. And this just goes back to P equals nRT. It doesn't matter the identity of the gas, just the number of moles. So that's why this works. Let's go over pH and KAs real quick, and buffers, in 3 minutes. All right, so hold on. Buffers. What makes a good buffer? Something that is a weak acid and its conjugate base. So, weak acid with its conjugate base makes a good buffer. So if he gives you a list, say like HCl plus NaCl, or let's say HF and F minus, which of these two would make a good buffer? The bottom one, right? Because it's a weak acid. Because it's a weak acid, it will bounce back and forth between these two. When we look at acids, bases, etc., we're looking at K values. So for acid, we're looking at Ka. Ka is important, and you also need to know, so pKa is important as well. When we look at buffers, we're looking at the Henderson-Hasselbalch equation, which is this. Basically, when you're selecting a buffer, you want something that is going to maintain the pH at a certain level. So when you select your buffer, all of these are going to change when you add acid or base, but it's not going to change your pH significantly. So what you need to know is that your pH of your solution is going to be pretty much your pKa. So when you're selecting a buffer, you want something that has a pKa similar to its pH. Remember, P is equal to the negative log. So pH is equal to the negative log of your hydrogen concentration. When I say concentration, that's molarity. To find your pKa, you're going to take the negative log of your Ka. Ka's will be given to you. You're not supposed to calculate those.
Can you repeat that?
So your pKa is the negative log of your Ka value. Ka values, you don't have to calculate. Those are given to you. Your pH plus your pOH is equal to 14. That's important to know as well, because he may say, all right, we have a 3.6 molar NaOH solution. What is the pH of this solution? Well, do we know the concentration of hydrogen? No, but we do know the concentration of OH. This is going to separate fully in solution. So what's our concentration of OH?
The negative log of 3.6.
So our concentration of OH is going to be equal to 3.6 molar, right? Does everybody see that? If we had 3.6 moles of NaOH in 1 liter, and then it separates, there's going to be 3.6 moles of OH. So then, this is our concentration of OH. We take the negative log of that, and we get our pOH. And then we can then find out our pH.
If it was like SROH2, then the concentration is 7.2 molar.
Wait, say that again?
So like if it has 2 hydroxide molecule.
Yes. It would be twice that amount. Exactly. Let's see if there's any last pieces of advice I need to give you. Know your strong acids and weak acids. So know which ones are strong acids. If you know which ones are strong acids, everything else is weak. It's a fairly simple redox reaction. So just make sure that you balance your number of electrons, and you should be good.
Will that be looking for the ON?
What?
Will that be the oxidation number for the redox reaction? Or the acid?
It'll be acid and coefficient. So let's say like this is the equation, balance it, and what's the coefficient? What's the number in front of?
We get to balance it.
Good luck. If you have questions, come ask me. I'll be up here for a few minutes. Celsius into water that is, we'll say like 20 grams of water that's 20 degrees Celsius. What is the ending temperature? Okay, so this is where you're going to go, the MCAT equals the MCAT. And you'll put a negative on the one that's going to be dropping in temperature. So this one starts higher.
Is it like Q equals negative Q, that type of idea?
So in this case, it'd be negative MCAT equals MCAT. Just because this one's going to have a negative delta T, because it starts at 58, you put it in something cooler, it's going to drop temperature, right?
Okay, that makes sense. So would the final answer then for something like this would then be a negative answer?
So your final answer would be a temperature between these two.
We're looking for the temperature, that's what we're solving for. Okay, so we would plug in like the 30 grams, we would find the number of moles. Is that how we would do that?
If you wanted, like sometimes this negative throws people off. So you could just say MCAT equals MCAT. Then find your delta T. It'll be the same on both sides, right? Because they're going to end at the same temperature.
Right.
And so then you could say, well, if the delta T, let's say you solve and you say delta T is equal to 15, you're going to say, well, this obviously dropped in temperature, right? We're mixing it with something colder. So it would drop to, we'll say the ending temperature would be 43 degrees Celsius.
Okay, so what would we plug in for the C value?
So that's the specific heat, and he'll give that to you. It's 4.18 joules per gram degrees Celsius.
But if you have water and water, then you can cancel it, right?
Exactly.
Okay.
I think the only thing I'm confused about is you would plug in the 58 degrees Celsius for the T, and the 20 degrees Celsius for the T. So how would you be solving for T, I guess?
So what I would do is I'd solve for delta T. If you wanted to go that direction, you could say delta T is temperature initial minus temperature final. And your temperature initial is given to you. And over here you would do the same, temperature initial minus final.
We're basically, it's for the first one we would know it's 58 minus 20, and the second one that's both delta T we're looking for. Okay.
Well, you would know, you know temperature initial for both of them. So this one would be T initial minus T final as well. Your T initials, these two are going to be different. Those are the ones that are given to you. But our T final is going to be the same for both.
That's what we're figuring out.
And that's what we're figuring out.
Minus T final, so we're just solving for the T final there.
Exactly.
Okay. That makes sense. Awesome. Thank you. And also one other question.
Ions, and you can add water as well. So those are the two things that you're going to be adding. That's not included in acidic. Right? So in an acidic solution, right? Since we're taking in acidic solution, you're going to add H pluses and water in the end. Those are the only two things you're allowed to add, right? So then you just need to balance it and see where you need to add those things. That's really all you're doing. So looking at this here, how are we going to, you guys know how to balance your chemical reactions. So I need to put some coefficients here, right, to balance out the atoms. So we're going to need to put those right here. So we have 2, we have 2 N's, 3 O's, 4. 1, 3, 4, 1, 2, 1, 2, 3. So it should have to balance as far as atoms, right? I think that should be balanced, right? So after you balance the equation, which one? 6, 7, 1, 2, 3, 4. So what else are we going to do? Is it balanced? 6 oxygen. There's NO3, 6, there's 7.
So 2 on CO2, 2 on H2O, and then 2 on CO2.
Oh, wait, hold on, sorry, you messed this up. Great, okay. So when you guys balance redox reactions, what do we ignore in the beginning?
Oxygen, hydrogen.
Okay, because we're going to be adding oxygens in the end, so we ignore the oxygen and hydrogens. Because in redox, those are rarely ever going to change their oxidation numbers, right? Like one of our rules is how we can determine their oxidation numbers, is we know that oxygen is always -2, hydrogen is usually +1, things like that. So we're just going to ignore those for now, because in the end we're going to add more, so it should balance in the end. So only focus on balancing your non-H's and O's. Okay? So we only need to worry about N for now. So our N's are good. That's all we need to worry about. Okay. Then you need to decide, look at which atoms are going to be changing their oxidation states. Okay, so let's go through and let's give our oxidation numbers here. So oxygen usually carries what oxidation state? -2. So this is -2 here. Okay, since I have 3 of them, that means a total of -6. So what does my N have to be? +5 oxidation state on N. Right? Everyone follow that? Okay, let's go here. Which one am I going to label first? Let's go with the oxygen, right? -2. What about my hydrogens? +1. And carbon? What's carbon going to be?
0.
0? Okay, what about this one? Yeah, carbon is 0 in this case because you name or you give oxidation states to oxygen and hydrogen first, and then whatever's left over is whatever is responded to those. That's the oxidation state of that carbon. Okay, what about this O? Which one are we going to label first, N or O? O always comes first, so. I actually think you label, if you have to decide, you label the H's first, right? You do H's first and then O's, if the order matters. But anyway, in this case there's only an O, so O is negative what?
2.
Negative 2, so what does N have to be?
Plus 1.
Plus 1. Plus 1. What about here? What's my C?
Plus 4.
Okay, here. Okay, so that's your first step, right? You balance the non-H's and O's, so we balance our N, and then you assign oxidation states. And then just look at every atom in here and see which ones actually change. Do we have some changes?
Yeah.
Which ones are changing?
Nitrogen and carbon.
Okay, so we have our nitrogen, right? It's going from +5 to +1. What else is changing?
Carbon.
Our carbon is going from 0 to +4. Right? My O's always are negative 2, so don't even look at those. My H's are always +1. So our H's and O's aren't going to change, so that's great. That's going to be easy. Okay, so if we have that, now we just need to decide how many electrons are being transferred total. Right, so this is total, so you need to take into account coefficients and how many of each atom you have. Does that make sense? So if I have a +5 here, but how many N's total do I have?
2.
So how many electrons do I really have, or what's my actual charge? It should be like +10, and then I go over here, what's my charge here? +2. So what's the difference between 10 and 2? So did it gain, or did it lose 8 electrons? Gain, because it's going more, going to smaller numbers, so more negative, right? So we gain electrons there. Okay, so then we look at our C. What happened? Is this the total? How many total do I have here? Sorry, total. 0. What about right here? +4. There's no coefficient, right? So it's just +4. Okay, so do these equal each other? What did we do here? We lost 4 electrons. Okay, are my transferring of electrons equal? No. Okay, so this is when you're going to have to balance the electrons lost and electrons gained. You want these numbers to equal each other. So how can I change that in my original equation so that I'm going to lose 8 on top and gain 8 on the bottom?
Carbon.
So we put a 2 here and we put a 2 there. Right? 2 times 0 is 0. 2 times 4 will be +8. You can change that, and then those numbers are going to equal each other. That's your goal with the electrons. Right? Okay. After that, what's our next step?
Adding
Right, we need to add the rest of the things. So after you get the electrons balanced, your next goal is to balance the charge on one side of the equation and the other side of the equation. So what I mean by that is, look at our charge, neutral, 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 right? Neutral, we have a negative charge here. How many negative charges do I have total? 2. So do you think I'm going to add water or H plus to balance out that charge? Okay, so I'm just going to tack on a 2 H plus here. Okay. And now we need a balance, and the other thing we can do is we can add H2O to do balancing. Right? Okay. If we look here, let's take inventory. I'm sorry, this is really close.
So how did you add H2O again? No, we did.
What was that?
Never mind.
Oh, so they erase it? Okay, so we're here, right? Is it balanced? First of all, let's decide if it's balanced. So we have 2 H's, we have 6 H's, right? 6 H's, we have 2 H's here. We have 6 O's, 6 O's, 8 O's. So we have 1, 2, 3, 4, 5, 6. Really, your last step is just balancing it, right? I guess I'm pretty sad.
For the 2 inch power water. 3.
Why does he have water in here?
So sometimes, so like if you don't have H2O in your products already, sometimes you'll need to add more water. Like if this wasn't here, right, we wouldn't have had to balance the H's and O's to begin with. We would just focus on the non-H and O atoms to balance Earth. Does that make sense? So I could have just left this out completely, and you guys would just add 3 H2Os. You could just add that to make it balance, because it would have been impossible to balance without H2Os. But since this one it already had H2O in like the original part, you guys didn't have to add new ones. But you can add new ones if you need to. Does that make sense? And it should always be on the opposite side of your H+. I don't know why you need it on the reactant side.
In this case, what did it balance off?
I guess a little bit of both.
Question?
Yeah.
So will the H plus always be on the reactant side?
It's going to always be on the side that has the negative charge. So you always have to put the positive charge where you have negative charges to balance out the charge of the ions. So first you balance the non. Are you guys getting confused? Do you want me to write down like what you do first?
That'll be great.
Yes. Okay, but did this make sense? We did this together. You walked through it. Was it okay? Okay, so your first step is what? Okay, so first you balance the non-HNO atoms, right? So we balance N. That was the only thing we worried about there. Then our next step was give oxidation states and calculate traffic. So does that make sense? You give the oxidation states and then you just see where the electrons go. And you remember you need the total. So after you see where the electrons are going, you want to make sure you balance the electrons. Okay, or after you balance the electrons, what do you do?
Balance the H plus, at H plus or H2.
H plus. And then our last step is that make sense? Does that kind of help you go through the steps? Okay. If not, like we just went through the example problems on the book, and there's some more example problems in the book, page 339. So if you read through those, like, just know the acidic ones, and if you can do these, you'll be totally fine for the question. Okay?
Captured effortlessly, that's the